find an antiderivative of rational functions. Okay, so aim to find an antiderivative for a rational function. Okay, so a rational function is of the form a rational function is f of x, say p of x over q of x, where p and q are polynomials. Okay, theoretically, we can explicitly write down an antiderivative for this. Okay, so theoretically, we can explicitly write down an antiderivative for f, but practically we can do this if we know all the roots of q. Okay, practically, this is possible if we know all the roots of qx. Okay. Okay, so today what we will do is we'll start with rational functions where we know the decomposition of the denominator, and then we'll show how we can write down an explicit antiderivative for f. Okay, so this method is this is a very methodical algorithm. Computers do that very fast. So you have to know what the computer is doing, so that when you are giving this problem to a software, you know what you are doing, or if the software fails, you know why it failed. Okay, so first of all, so in this method, we first divide p by q to get f of x equals, let's say, u of x plus r of x over q of x, okay, where u, r, q are polynomials. And when you divide p by q, okay, and degree of r is strictly less than degree of q. Okay, so this means that p of x is equal to u of x, q of x plus r of x. Okay, so this is the usual polynomial division, and you make sure that here what you obtain is either 0 or the degree is strictly less than q. Sometimes, to avoid saying an extra sentence, we agree that degree of the 0 polynomial is minus infinite, and then this is enough to say that degree r is strictly less than q. Antiderivative for this is easy. Okay. Antiderivative for this is easy. It's just polynomial differentiation. So it remains to solve the case when the degree of the numerator is less than the degree of the denominator. Okay. So the problem is to find an antiderivative for p of x over q Q of x when degree of P is strictly less than degree of Q. Okay, so this is the setup. Okay, so first step, well, this is actually the first step, but okay, let's see, suppose we agreed that we'll start with this one. Then we factorize Q of x. Okay, so this is easily said, but in practice, this is not easy. There's a huge history in mathematics trying to find roots, trying to understand roots. We still don't know a lot of things about roots. But here we know the following. If Q of x is a polynomial, okay, let's say, you can always make sure that the leading coefficient is 1 plus a0 with each ai a real number. Okay, so you can also have a number here, but then you divide everything by that number. You obtain a polynomial with the leading coefficient 1, and of course the zeros don't change. Okay, you are just multiplying a polynomial by some constant. Then Q of x is equal to product of some x minus the root, say alpha 1, we don't know, some power m1, x minus alpha r, some power mr, and then we have x squared plus, okay, I'll also invent some numbers here, beta 1 x plus alpha beta gamma, gamma 1 to some power, again, say L1. So I made this extremely complicated. X squared plus beta t x. Okay, so this makes it look very scientific. T, okay, where alpha 1, alpha r are real roots, m1, mr are positive integers. Well, also L1, LT are positive integers. And beta I, gamma I are real such that, well, the discriminant must be negative. So what's the discriminant? Beta I squared minus 4, gamma I is negative for I equals, in my case, t. Okay, so this means we can factor Q of x as a combination of linear factors. So linear factors are these things to some power, and irreducible quadratics. Irreducible quadratics. Okay, so these are quadratic equations. They don't have real roots. So irreducible here translates in everyday language. They don't have real roots. They have, since the coefficients are real, they have complex conjugate roots. Complex conjugate roots. Okay. So first, theoretically, we know this. Practically, to obtain this factorization is, well, practically it's impossible in most cases. Okay, if the polynomial is cooked up, so by trial and error you can find it. If the degree is small, you can find out if you can write it like this. So, for example, if alpha 1 is a real number, say P over E, okay, so it's not easy to detect it and write it just alpha 1 there. So in our examples, for the purposes of understanding this technique, all real roots are going to be integers so that we can easily factor these things. Okay? And after you factor these things out, since we are going to do this by hand, we will have only one factor like this. So we will recognize that the discriminant is negative. It doesn't have a real root. Okay, so this is the theoretical part. But in practice, we will have only one or two terms here and maybe one or two terms here. Okay, so let's see what we do after this. Okay, then we consider, okay, so next we have f of x equals p of x over q of x. Okay. So here we have complex conjugate roots. So let me say, for example, okay, so x squared plus b1x plus alpha 1 is equal to x minus, I don't know, let's say theta 1, x minus, again, theta 1, but complex conjugate. Okay, so the roots of this polynomial are these real numbers and also these complex numbers. Okay, so the general theory says that if the denominator vanishes at some point, then the function has certain properties which you will learn in complex analysis. But borrowing results from there, that theory tells us that around each singularity, when the function is not defined there, we call it a singularity. Around each singularity, we can write the function in a specific way. Okay, so here we are going to borrow that result. Okay, so for each factor of the form, let's say, let me copy here what I had. Okay, so here I used alpha. So let's say x minus alpha to the power r. Let me denote all of them like this. Write a1 over x minus alpha plus a2 over x minus alpha square plus ar over x minus alpha r, where alpha I are real numbers to be determined. Okay, so that's the whole idea here. So this technique has two bottlenecks. One is to factorize the polynomial, which is next to impossible. The second difficult thing is if you have too many factors, then to determine these numbers is also very time consuming. Okay, so if the power is 1, you only consider this one. If the power is 2, you consider these things. And for each factor of the form x squared plus, okay, let me write the general thing here, plus q with p squared minus 4q negative, right? So generally we write this as b1x plus c1 over x squared plus px plus q plus, okay, here I wrote the second one, so let me write the second one also, plus c2 over x squared plus, we have, let's say, again we have, say the power is m here, px plus q squared, so you have all these things, bmx plus cm over x squared plus px plus q to the power m, where again bi, ci are real numbers to be determined. Okay, so the next step is also very easy. Okay, now add up all the above expressions and set the sum equal to f of x, p of x over q of x. Okay. Now you have an identity which holds for all x. Okay, so this identity, notice this is important. Well, this is theoretically important. When you are doing calculations, you assume this anyway. Notice that this equality holds for all x in R for which the denominator is different than 0. Okay, so let me just say that. Okay, now determine this. This makes it possible to determine all the above constants. Okay, one way to do this is, well, the longest way is on the right-hand side, you see, well, okay, so generally we write this on the left-hand side equal to all these sums. The sum of all these things is a rational function. You bring it to common denominator. What is the common denominator here? You can immediately tell the common denominator is going to be qx. Okay, so in order to sum these up, I have to bring these things up to this power. Okay, and then I have to bring these things up to this power. So I have something, a polynomial divided by x minus alpha to the r, this to the power m. Now, in order to bring them to the same denominator, I have to multiply these things. So eventually, in the denominator, I obtain q of x. Okay, so the denominators are the same. Therefore, the numerators must be the same. On the left-hand side, on px, the numerator is px. All the coefficients are known. On the right-hand side, you have a polynomial of exactly the same degree. Okay, but the coefficients are combinations of the linear combinations of these constants, a's, b's, and c's. So coefficient of x to the n is equal to the coefficient of x to the n here. On this side, you have a number. On this side, you have this linear expression in these constants. So you obtain n linear equations in n unknowns, and theoretically, this is solvable. Well, sometimes it's not solvable. Not every linear system is solvable, but the general theory, which we are borrowing from complex analysis, tells us that this system is solvable. Well, to solve a linear system is theoretically totally trivial. Okay, you just consider the coefficient matrix, find this inverse, multiply it with the other side, and you obtain the result. Okay, so but to find the inverse of a matrix is very time consuming. There are other methods to solve this. So this is the second bottleneck. Okay, first one is to factorize this, and the second one is this. So in the examples, these ones will be easy. Okay, so it will have a few terms just to demonstrate the method. And then when you come here, you will have only a few numbers here. So instead of solving this by determinants, you can just use elimination or something else and determine the coefficients. There are other methods that we use in the old times to determine the coefficients, but now computers are very fast. In fact, you can give this polynomial to some software and bypass this and say convert it to partial fractions. So it immediately gives you this. Okay, so when you write this thing, that part is called, okay, this sum equal to this. Okay, so this is called the partial fraction decomposition. This is where the name comes from. This is called the partial fraction decomposition. Okay, now, why did we do this? Well, first of all, if we have this, now we equated this to sum of things of this form and of this form. If you have this, you can easily integrate this. Okay, this is logarithm, and these are rational functions. Okay, this is derivative of 1 over x minus alpha up to some constant. This is derivative of 1 over x minus alpha to r plus 1. Okay, up to some constant. So this thing can easily be integrated. So this part, well, this is the tricky part. But suppose here that p is 0, q is 1. Okay, so everything like this can be converted in new coordinates to x squared plus 1. Okay, so suppose this is x squared plus 1 with new coordinates. Then x over x squared plus 1, you can integrate this. Okay, by substitution, because the derivative of this is here. Okay, so you can also see it here, but generally we don't do it that way, because you see the derivative of this is here up to an additive constant. This C1 may not be correct, okay, but you just multiply this thing by some number and add or subtract. So the derivative of this is here, plus some constant is left. Okay, and then that constant over this, when you integrate this, change coordinates, you will see that it is arctangent. Okay, because in general, this is x squared plus 1. A constant over x squared plus 1 is arctangent. Okay, but this one is tricky because there's no method for this. Here you use a reduction formula. We will do that. You use integration by parts, and you can show that this thing can be written in terms of these things. Okay, so this thing can be written in terms of the previous one. That can be written in terms of the previous one. So theoretically, we can integrate these things. So that's how you write the computer software. We have all this mechanism. So when you are writing the computer software, this part is totally trivial because computer solves this. So when you are writing the computer software, this is the part where you have difficulty because nobody knows how to factorize these things. Okay, so this is the theoretical part. So let me add one last thing here. Finally, you integrate the partial fractions. Okay, so this thing is best demonstrated on examples. So, okay, I'll do examples with this is the most boring part about partial fractions. If you try to explain the general theory like this, it looks impossible. But in the exercise, in the examples, not every case appears. So examples are easier. So let me start with some examples. Okay, so let us start with a function like this where the factorization is already given. Okay, so I did this with computer, so. Okay, so the factorization of qx is already given. The denominator is of degree 2. The numerator is of degree 1. So this is the setup for partial fractions. Okay, so I write this as, I have only one factor here, so this is x plus 3. For this one, I have another 2x plus 1. Okay. Now determine a and b. Okay, let's see. If you can't think of anything else, this is what you do. You bring these to common denominator, a times 2x plus 1 plus b times x plus 3. Okay, and then you have x plus 3, 2x plus 1. Okay. Now you look at this part. This is 2a plus b times x plus a plus 3b divided by x plus 3, 2x plus 1. Okay. You see the denominators are the same, so numerators must be the same. Therefore, 4x plus 1 is equal to 2a plus bx plus a plus 3b. And we remind ourselves that this is true for every x. This means the polynomials are identical. Okay, so this means the two polynomials are identical. Okay. So that means the coefficients are the same. That is 2a plus b is equal to 4. A plus 3b equals 1. Okay, so solve this system. Now, solve this system. Okay, so that's generally how the computers do this. Okay, so you can do anything you like here. So I leave it to your taste to solve this. You can multiply this by -2, add it here. So that gives you what b is. Once you know what b is, you put it here. You find a. So if you are esoteric, you can consider the coefficient matrix 2, 1, 1, 3. Find its inverse. Multiply the inverse by the column vector 4, 1. That immediately gives you what the unknowns a and b are. Okay. Another way is you can do this here. You see that on this I can multiply both sides by x plus 3. Okay. So then when I multiply both sides by x plus 3 here, this doesn't appear. This doesn't appear. So now I can put x equals -3. There's no division anymore. I cancel. When you put x minus 3, this is 0 because I multiply this by x plus 3. When I put x equals -3, this disappears. And here, you put x minus 3 here, and that gives you immediately what a is. Okay? You do the same thing with this one. So now you know what a is. You put that number here. You multiply both sides by 2x plus 1. Okay, so there is a factor of 2x plus 1 here, and this is erased. Now you put x equals -1/2. This becomes 0, and this becomes a number. Okay, and that gives you immediately what b is. Okay, in simple examples, you can use that trick if you are doing this by hand. Okay, so what you do with the computer is almost every software has a command. You give this polynomial and you say convert this to partial fractions, and you immediately get the following. Okay, so here you get, so what did I find? A is equal to 11/5 and b is equal to -2/5. So 4x plus 1 over x plus 3 2x plus 1 is equal to 11/5 x plus 3 minus 2/5 2x plus 1. Okay, so software will convert this to partial fractions and immediately give you this one. Well, if you are using software, you don't generally do that. You give this to a computer and say integrate it, you get down to derivative. But in between, this is what the computer is doing. Okay, so why did we do this? We want to integrate this. Hence, finally, integral of 4x plus 1 over x plus 3 2x plus 1 dx is equal to integral of 11/5 dx over x plus 3 minus 2/5 dx over 2x plus 1. Okay, so the whole idea was to bring the integral to this form where we can now easily integrate. So this is 11/5 ln x plus 3. Well, actually, we want the absolute value here minus. Well, if I have this, I think I'll have 1/5 ln 2x plus 1 If I take the derivative of this, I'll get an extra 2, and that is here. And then, of course, you just put your constant. You never know when you'll need it. Okay, so this is demonstration of partial fractions on a very simple example. So let us do, now in the next example, let us have squares here and see what happens. How time flies. Okay, so this time we have 3x plus 1 over x minus 1 square, x plus 1 square. No, I had this one, x squared plus 1. Okay, so now I'm introducing quadratic forms. Okay, so this is, now the general theory says for this one I have a over x minus 1 plus, I think I'll use b over x minus 1 square. So I go up to this power, but always constants here. And for this one, I have cx plus d over x squared plus 1. If I had another power here, I'll have another term here. But this is what I have. Okay, so here you see you can use that finger crossing, whatever the name, covering up method. We used to have a name for this thing. But you see, you cannot, by that method, you cannot find this coefficient, because when you multiply both sides by x minus 1, here you still have one x minus 1 in the denominator, so you cannot put x equals 1. But you can multiply both sides by x minus 1 square. Okay, so this will disappear, this will disappear, and you will have x minus 1 factor here and x minus 1 square factor here. Now when you put x equals 1, this part will be 0, and here you will have 4 over 2, 2. So b is going to be 2. Okay, so you put 2 here. So this reduces the amount of time you will later use in solving the linear equations. Instead of solving 4 unknowns, you immediately know what this is. And then from there, now you have 3 unknowns. Okay, so let's say bringing to common denominator and equating numerators. So what we have here is that 3x plus 1 is equal to a plus c x cubed plus minus a plus b minus 2c plus d x squared plus a plus c minus 2d x plus minus a plus b plus d. Okay, so I know that now this is equal to 0 because there is no x cubed here. This is equal to 0. There is no x squared here. This is equal to 3, and this is equal to 1. Okay, so now we have 4 unknowns in 4 linear equations. The general theory guarantees that this has a unique solution. Okay, so that part we didn't do. So easiest way to understand the general theory is to look at complex functions, but we are not doing it. There are elementary proofs of this using just high school algebra, but it is long, so that's why we don't show it here. So you just have a religious belief that every time you have a system like this, it has a unique solution. It does have a solution, and the solution is unique. So with that faith, you attack the problem and you solve the equations. So when you solve them, you find so where is a is equal to, of course, you don't generally do this in this order, but this is what you get. So you see, I said b is going to be 2. So if you solve this, you also get b is 2. C equals 1 over 2. and d is equal to minus 3 over 2. Okay, so putting these things in, you have, so integral of 3x plus 1 over x minus 1 square x squared plus 1 dx is equal to, okay, so I'll write these things, minus 1 over 2 integral dx over x minus 1 plus 2 of dx over x minus 1 square plus integral 1 over 2 x minus 3 over 2 over x squared plus 1 dx. Okay. Okay, so we do this one by one. So actually this thing we can write as follows. You see this is equal to 1 over 2 integral x over x squared plus 1 dx minus 3 over 2 integral dx over x squared plus 1. Okay, so now each of them has a simple antiderivative. Okay, we can integrate all of these things. So the answer, let me copy the answer from here. Minus 1 over 2 ln absolute value of x minus 1 plus, I have, so why do I have plus here? 2 over x minus 1. If I take this, I must have minus here, right? If you take the derivative of this, what do you get? You get minus 1 over x minus 1 square. So let's put minus here. And this one is plus 1 over 2. I put 2 here, so I put another 2 here. So this is ln 1 over 4 ln x squared plus 1. So it's already it's already positive, so I don't need to put absolute value. The other one is arctangent, minus 3 over 2 arctangent x plus our integration constant. Okay. So let me show one more thing. So what would happen if I had square of a quadratic term? Okay. Okay, so suppose we have x over x squared plus 1 to the power n dx. So what is this? So here we put u equals x squared plus 1. Then du is equal to 2x dx. And this becomes 1 over 2 integral du over u to the power n. Okay. So this thing is equal to, if n is equal to 1, we get logarithm 1 over 2 ln absolute value u plus c, which is equal to 1 over 2 ln x squared plus 1 plus c if n equals 1. So here n is a positive integer. N is a positive integer. If n is 0, you are just integrating x. If n is negative, then this is up there. You are integrating a polynomial, so we are not interested in that. If n is strictly larger than 1, then you have 1 minus n, 1 over u to the n minus 1 plus c, which is equal to 1 over n minus 1, 1 over x squared plus 1, n minus 1 plus c if n is strictly larger than 1. Okay, so this case is easy. So what remains, you see when we have a quadratic term, here we have this x and this d. So this, if I have a power here, I understand how to integrate this part. So it remains to understand the other one. So that is where the trick is. Suppose now, let us call it in equal to integral dx over x squared plus 1 to the power n. Okay, say n is strictly larger than 1, because if n is 1, we know that this is arctangent. Okay, so I1 is arctangent x plus constant. So now we want to understand this. So integrate by integrate by parts with, let's see, u equals 1 over 1 plus x squared to the power n, all of this, and dv is dx. So this is the trick you play when you don't know what to do. Okay, so you want to find the antiderivative of this, so it's difficult, but it's taking its derivative is easy, so you take its derivative, but there's a price you have to pay. The price is not very bad. du is, okay, so let me skip this intermediate value. You integrate this by parts using this, substitute this in, and you get in equal to x over x squared plus 1 n plus 2n times integral x squared dx over x squared plus 1 n plus 1. Okay, but this one you can write as follows. You can write this x squared plus 1 minus 1 over x squared plus 1 n plus 1. So it becomes, this one cancels. You have x squared plus 1 to the power n minus 1 over x squared plus 1 to the power n plus 1. Okay, so now this becomes x over x squared plus 1 to the power n plus 2n I n again minus 2n I m plus 1. Okay, so this thing is equal to in. Solve for in to get in equals x over x squared plus 1 n. Well, I want to do this. Okay, let me again skip a power. Solve for in. Okay, let me write this. In is equal to 1 over 2n x over x squared plus 1 n plus 2n minus 1 over 2n in. In plus 1. Okay, solve for in plus 1. Okay, in plus 1 is this. Okay, so the larger one, we managed to write the larger one in terms of the smaller one. Okay, just replace n plus 1 by n to get a clean reduction formula. This is also a reduction formula, but generally we don't want to say that I'm reducing the n plus first case to the nth case. This is practically useful, but just for aesthetic reasons, I want to say that in can be written in terms of in minus 1. Okay, so finally the formula is this. In is 1 over 2n minus 1 x over x squared plus 1 n minus 1 plus 2n minus 3 over 2n minus 2 I n minus 1. This is true for n larger than 1. So if you are writing a software, this is how you do the reduction. Okay. So you see this part can be integrated, okay, because the derivative of this is here up to a constant. So this can easily be integrated. And you have this one. Now you again reduce it until you go up to n equals 1, and when n equals 1, it's also integrated. It can also be integrated. So this tells you that everything can be integrated. Except that I think we have to do one more thing. Okay, so I'll write an interesting example, but before that, well, maybe I should write it here. Okay, so you see that we gave the reduction formula in this form, but what if we have a general polynomial here? Let us convince ourselves that we can always change coordinates. Okay, so changing coordinates means substitution, remember? We can also do a substitution to make it look like that, but that's the usual thing that is known even from the time of Babylonians. So let Q of x or Q of x equal x squared plus px plus q with p squared minus 4q negative. Okay, so then we complete this to a square, x squared plus 2 times 1 over 2 px. So I add the square of this 1 over 4. Now this becomes a complete square, but I have to subtract 1 over 4, 1 over p square here. Okay, so this one and this one, p square. So p square plus q. Okay, so this part, the reason I did this is because 1 over 2p square plus, okay, so now I have this thing. So this is 4q minus p squared over 4. Okay, so observe that this is, call this m or call this a, this is positive. Okay, because of this thing. Okay, so I have x plus 1 over 2p squared plus a, or let's call this a squared. Okay, now I can divide everything by a squared. So this is a squared. So I have x plus 1 over 2p over a squared plus 1. Okay, call this your new x. So this is a squared times x squared plus 1. Okay, so using substitution, you can write every irreducible polynomial as x squared plus 1. Okay, so the techniques we have explained so far now gives an algorithm for finding the partial fractions decomposition of every rational function, provided that you know an exact factorization of the denominator. Okay, so that part, finding an exact factorization of the denominator, is tricky. Most of the time you can't find it. So in the remaining few minutes, let me give a nice example where we get a formula exploiting these facts. Okay, nice problem. So let's finish this topic with a nice formula. Okay, so let Jm be integral from 0 to infinity dx over 1 plus x squared n. Okay. So we know that this is equal to Jn is equal to, now I'm using this reduction formula. So using the previous reduction formula. Reduction formula for in, okay? Because forget about the integration limits. we have in here. So we can write it as follows: 1 over 2n minus 1 x over x squared plus 1 n minus 1 from 0 to infinity plus 2n minus 3 over 2n minus 2 jn. Okay? When x is equal to 0, because of this, we get 0. When x goes to infinity, because the degree of the denominator is larger than the degree of the numerator, the limit is 0. So this part does not contribute anything, and I end up having 2n minus 3 over 2n minus 2 jn minus 1. Okay. Well, since I know that jn is equal to this, now repeat. Now, I don't have to do this one. I just say that if I have n here, I have these things here. So instead of n, I put n minus 1. So I get 2n minus 3, 2n minus 2 from here. But this thing is now 2n minus 5, 2n minus 4, jn minus 2. So this goes up to the last one where I have 2n minus 3, 2n minus 2, all these numbers. And what is the last one? So I keep subtracting an odd number, increasing odd numbers from the larger one, from an even number. Okay, so I'll stop when I get 1. Okay, from an even number, I subtract 2, 4, 8, etc. I stop when I get 2, and here I have j1. But j1 is arctangent from 0 to infinity. Okay, so that's pi over 2. But j1 is pi over 2. Okay, just evaluate that. So we found integral from 0 to infinity dx over 1 plus x squared to the power n is 2n minus 3 over 2n minus 2, 2n minus 5 or 2n minus 4, 1 over 2, pi over 2. Okay, so depending on what n is. So here n is larger than or equal to 1. Okay, so n is larger than or equal to 1. Okay. So when n is equal to 1, you don't have these things. Okay, so you just have this one. When n equals 1. So this is when n equals 1. So let's say n is strictly larger than 1, because then n equals 2, you start from having here. When n equals 2, you just have 1 over 2, pi over 2. Okay, so I have other examples, but you see all these examples, we covered all cases. Okay, so let me see if I am missing something. Okay, so the rest you can, that's all for integration using partial fractions. So as I said, this is a technique which has an algorithm. And if you are using a computer, the only thing you have to give to the computer is an exact factorization of the denominator. Okay, if it doesn't have a nice factorization, the computer won't be able to do it. Okay, let's stop here for 10 minutes.